Okay, question number 2 says a constant pressure, so I'm just going to note that that's a constant. A sample of gas occupies 420 milliliters, so there's my V, at 210 Kelvin. There's my T. What volume, so my V2 or V prime is my question mark, does the gas occupy at 250 degrees, or 250 Kelvin? So there's my T2. All right, so my graph. Well, what happens to if I change the temperature, what happens to the volume when the number of particles and the pressure are constant? So if I make the temperature higher, what happens to the volume? Well, if the particles are moving faster and we don't add any more particles and we want to keep the pressure the same, then the balloon has to get bigger. Okay? For every statement, so we've got a for every 420 milliliters of gas, there is 210 Kelvin. And then on the other side, we've got for every blank milliliters of gas, there is 250 Kelvin. Okay. So we want to know, well, if the T goes up, then the V goes up. And I can see that on the graph here, right? If the T starts here and then moves here, and as the T goes up, if I look at those two, the V also goes up. So this went up by about 20% or times 1.2-ish. Yeah, about 1.2. And this goes up by 1.2 as well. So 420, a tenth of that would be 42. 20th of it then is 84. And that would be 504. So 504 milliliters. Sig figs, we only need 2 if we were being technical. So that would be 5.0 times 10 to the second milliliters. And then last, well, what's actually happening here? Well, the balloon's getting bigger. Not by much, but it's getting bigger. I'm just going to draw a balloon, or as my class likes to call it, a mushroom cloud. And it gets a little bit bigger. And the reason it gets a little bit bigger, if I start with, let's say, 5 particles on the inside, the reason it gets a little bit bigger is not because we got more particles. It's just because these particles in the balloon, let's make this 2 pressure. Now let's make this one 2 pressure moments because the pressure doesn't change, right? What does change is that these particles are moving faster. Okay. So there's my stuff. I'm going to show the outside pressure too. So there we go. 1, 2. We got a bunch of stuff moving around here. Randomly around. Outside of the balloon, still the same temperature. And it looks like we're in good shape. Okay. Okay. And apparently all of my explanation got paused, but here's what's going on is that the pressure and temperature are both going up because as the particles move faster, they hit the sides of the container more often. 120 kilopascals at 400 K. If we move that to 600 K, it goes up by 1.5 times as much. So this also goes up by 1.5 times as much because they are directly related. We know that from the graph. We know that from experimental data. And here's what this looks like at the bottom. Notice the volume of the balloon. I tried to make it the same size. All that happens is the inside particles are moving faster, and therefore they are more likely. We got 3 pressure moments versus 2 pressure moments here. Okay, this last one, we've got 3 things to consider. It says a sample of fluorine gas occupies 810 milliliters. So that's my V1. 270 K. There's my first temperature. And 1 atmosphere. There's my pressure. What volume, so the V2 is my question mark, right? Does the gas occupy when the pressure is doubled? So that means that my P2 is 2 ATMs. I'm just going to mark that down. And the temperature, T2, is 400 K. Okay, this one's a little trickier. Okay, we got to compare the volume to both pressure and temperature. Okay, so if pressure and volume are, if we're comparing those two things, we've got N and T to think about. All right, so if I can't change the number of particles and the particles move the same, then as the volume goes up, they are less likely to hit the sides of the container. So this is an inverse relationship. So that means as P goes up, which is what's happening, the V will go down. And then V and T, well, we just discussed this just a few minutes ago. P and N are the same. Temperature goes up. Pressure stays the same. That means the volume's got to go up. Okay? So this means that as the temperature, as the temperature went up, it did go up, the volume, or the pressure, or the volume also went up. Forgot what we were studying for there. So this is a little trickier now. We've got to think about a bunch of stuff. So we've got, for every 810 milliliters at 270 Kelvin, there is 1 atmosphere. Okay? And then down at the bottom, we've got for every, well, the volume is the thing I don't know, some amount of milliliters at 400 K, there is 2 atmospheres. Okay, so now let's figure out, okay, well, this is going up by, and I think I'm going to need a calculator to do this one. I know that's a bad word, but about 1.5. This one's going up by 1.5. And then, let's get a different color. This one is doubling, right? So this is times 2. Okay. Now the thing is that if I'm comparing this pressure volume, that means that this is going up by 2, but that means that the volume then is going down by a factor of 2. And then coming back to this, my T and V, as the temperature goes up, the volume also goes up. So this is going up by 1.5. So I can do it either way. 810 divided by 2 is 405. Half of 405 is, if I'm multiplying it by 1.5, is 202.5. So that comes out to be 608. So it did go up. It went down because the factor, if you think about it this way, this factor was larger than this factor. Okay. We got a lot to show in this picture. Let's figure out what remains constant in this. Well, I noticed here that N was constant. I noticed here that N was constant. So the only thing that's staying the same is the number of particles. Okay. The pressure doubles and the volume goes down. So let's start with the volume. We got a big balloon to start. And on this side, I don't have quite as big a balloon. Okay. The temperature goes, the number of particles stays the same. So let's make the particles in here. We gotta put, I don't know, let's say 6 particles in here. And let's put the same 6 particles over here. Notice that they are closer together. The pressure goes up by 2. So let's make 1 pressure event here and 2 pressure events here. And you notice that the temperature goes up by 1.5. We don't really have a way to make it 1.5. So let's just make it twice as big. I'm going to try to randomize this a little better. There we go. Moving in all random directions. Okay. And what have we not accounted for? We've got the volume went smaller, right? So the balloon is smaller. We've got that the temperature went up, so more swooshies. We got that the pressure went up, 2 particle moments, or pressure moments, 1 pressure moment here. And the number of particles stays the same, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then the only thing that we probably want to do here is throw some something on the outside, some air particles on the outside, because they're holding that in. Same amount on the outside, still the same amount of pressure on the outside. The only thing that changed was that on the inside of this it went up. Okay, and we probably should say that a circle is air or gas, either way. Okay, I hope that helps.